We have a few things to cover today, so I'm going to dive right in. First, as always, I want to just kind of quickly review the troubleshooting lecture and see if there are kind of any questions or points that were unclear there. But we'll try to move through that relatively fast. And then we'll talk about, briefly about kind of what you worked on for your projects last week, and then what we're hoping that you can get done this coming week. And then we have another lab. This is a fun one. It's on debugging neural networks. And so I'm going to ask you to actually take some really bad neural network code that I wrote and make it better. And then we have a great guest lecture at the end. Okay, so troubleshooting lecture. I think there's kind of the core of this lecture was in two parts. The first is thinking a little bit about why troubleshooting is a hard problem. And I think there the summary is kind of, one thing that makes deep learning different than traditional machine learning or traditional software engineering is that it can be really, really difficult to even tell if you have a bug. And once you know that your performance is bad, there's many different contributing sources of error that could be causing that. And on top of that, to make matters worse, you can have a single hyperparameter that small fluctuations in its value cause big changes in performance. So all these things are sort of contributors to why this is such a hard problem. And so because of this, because there's many different sources of the same error, the key idea that I tried to get across was really the thing that you should do is you should start as simple as possible. So start with the simplest possible version of your model and your data, and then gradually layer on complexity, kind of one layer at a time, so that you can rule out the sources of error as early as possible in your process. And then I talked through a strategy for troubleshooting deep neural networks. There's a few steps here. The first was, again, starting simple. So choosing the simplest version of your problem, simplest version of your data. Then, you actually go and implement that. Once you've implemented it and you convince yourself that, you're pretty sure that there are no bugs there, then you go and evaluate it on your validation or your test set. And based on what that says, then you can go and make improvements to the model and the data set, or you can tune hyperparameters. Or maybe your performance meets kind of what your expectations are, and you can be done and sort of try to start deploying it. So starting simple, again, there are a few steps here. Simple architecture. To start, there's only a few model architectures that I really consider for like version 0 of the project. I would almost always start with atom optimizer, no regularization, normalized inputs, and if you can, a simpler version of the problem. So maybe a small synthetic data set or fewer classes or something like that. And again, this is all in service of making sure that you can get something working end-to-end right away and convincing yourself that there are no bugs in your pipeline. All right, and so once you've made some simple choices, then the next step is to actually go and implement that model and debug it. And so the first thing you need to do is make sure that it even runs, and kind of the main technique here to make sure that that works is to step through things in a debugger and watch out for like making sure that shapes are all the right sizes and that you're not casting things incorrectly and things like that. And once the model runs, then one thing I always recommend doing is overfitting a single batch of data. What this means is driving loss all the way to 0 on a single batch of data. And this will catch a lot of errors, especially in sort of your data preprocessing and things like that. And once you've convinced yourself that you can overfit a single batch, then ideally you can compare what your model, the score that your model gets to some sort of known result. And there are different levels of the quality of known results, but even something as simple as just a heuristic baseline or the average of your model's outputs is still giving you value in knowing that your model is doing something useful at all. Okay, so once you've implemented your model and you feel like there's probably no bugs, then the next step is to look at the performance of your model and decide what to do next. And so the key idea here is that if you look at your error on your test set, you can break that down into some components. The first component is something called irreducible error, which just means sort of the error that you're not really expecting your model to do better than. And then on top of that is bias, which is how much you're underfitting your data set. Variance, which is how much you're overfitting your data set. Distribution shift, which tells you kind of how far apart your training and test distributions are. And then finally, overfitting to your validation set, which can happen if you optimize hyperparameters on your validation set too many times. Okay, so now you've evaluated your model's performance, and you've gotten a sense of which of these components is the main contributor to the error. And then the next step is to figure out how to improve your model. And this is the order that I recommend doing it in. It's first you address underfitting. So first you make sure that you can get train error as low as you want it to go. Once you can do that, then I move on to overfitting. So then make sure that the gap between train and validation is not too large. Once you're not overfitting, then you can move on to distribution shift. So if you're in the situation where you can't collect infinite data from your test distribution, then just making sure that there's not too big a gap between the data you do have from your test distribution and the data from your training distribution. And then finally, and only infrequently, evaluate performance on your actual held out test set, and just see if you've overfit to your validation set by trying too many hyperparameters. Okay, and then the last topic that I covered was just how to think about hyperparameter optimization. And there's two components to this. One is how do you pick which hyperparameters to optimize? And there's kind of a list in the slides there of how I typically think about that. But it tends to be very problem dependent, and so there's no really easy answer to that other than just try things. And then once you've picked which hyperparameters to optimize, how do you actually optimize them? I think early on in a project, you can even just do a grid search, or if you want to be fancier than that and better than that, you can do a course-defined random search. And as your organization gets more mature and your project gets more mature, then you can consider using Bayesian hyperparameter optimization, which generally works better, but can be kind of hard to implement and can introduce bugs of its own. Cool. That's the quick 5-minute summary of the hour-and-a-half lecture. I'd love to hear if there are any questions about the lecture, things I just covered, or things that were in the video that you were curious about. Yeah.
So, since I'll start from the very end. Of course, this should be done at the very end of the development process, but of course, to find random search implies that you have, this space of hyperparameters. How do you even define the space? Let's say I can think of learning rate and bigger and smaller learning rates, but there are also things, type of initializations and type of things on which defining the order itself is hard. So how do I go about bisecting those options into sub parts?
So is the question for things like what type of layer should I use? How do you think about dividing that up? Yeah, I think for things like that, so generally for these hyperparameter optimization methods, generally this is useful when you have hyperparameters that come from some continuous space, or at least there's a large number of them and they have some sort of ordering. For hyperparameters, that are more like design choices of your algorithm, like which optimizer should you use, or what type of layer should you use, which nonlinearity should you use. Usually there's only a few choices that you might want to try, and so you can just try each one of them. Yeah, and I mean you can't try every single possible type of layer, for example, but this is kind of where you need to use intuition and figure out which ones are most likely to be successful. Yeah.
When you talk about trying different things, when you try one sort of configuration or hyperparameter configuration, do you need to train it for that for the whole number of epochs, or is it a good indication to see how it's doing in the beginning? Is that going to be a good indication of how it's going to do, just to save resources and to be able to try different configurations?
Yeah. So unfortunately, you can't always tell from the first few epochs of training which hyperparameters are going to end up performing best. That said, I think a lot of people in practice do use that because often it's a good indication, and you can often throw away some hyperparameters that are just clearly not learning at all. So if you're early on in this process and you're just trying to figure out which like at a very coarse level what your learning rate should be, then if something just doesn't train at all for the first few epochs, then you can probably just throw that away. I think also some of the Bayesian hyperparameter optimization techniques do like clever things with sort of varying which hyperparameters they're training at which stages of training. Yeah.
So for this hyperparameter optimization, should we consider some other kind of time model to do it, or to do it with your original model, with a complex model with all the data? Or you want to, because something like auto augment, which I've read about, where they use separate separate techniques to work on a time model and update your original model. What do you suggest then, or just doing searching for the best hyperparameter?
Yeah. Not totally sure I understand the question.
Like we search on our existing model with all the data set that we have, or should we do like take a set of samples and then do a different model and then search?
I like things, putting aside things like auto augment, if you're just doing standard hyperparameter tuning, depends on which stage you're at in the project. Like if you're, if you're sort of still working on a really simplified version of your problem and you still can't get your training error low enough, then I would keep working with that simplified version of the problem until you can find hyperparameters that do get your training error low enough. And then as you move on, you might need to, like your data set will get bigger and more complex as a function of just being better at working with the simpler data set. And then at that point, when you're doing hyperparameter searches, I would use the kind of the full version of the data set that you're working with at that time. Yeah.
So maybe in terms of building on that, what happens if the hyperparameters that work for the smaller set don't work for the larger set? How do you go about debugging that?
Yeah. So this does happen. Usually I found that that the hyperparameters you choose for the smaller and simpler data set are a reasonable starting point, at least for the bigger data set. And so, often like the process of hyperparameter optimization in practice looks something like, you just sample hyperparameters like on an exponential grid at first, because you have no idea, like should the learning rate be 1 or should it be like, 10 to the negative 6 or something. And so you'd sample like 1 and 10 to the negative 1 and et cetera. And then, once you have a sense of like, okay, maybe it's around 10 to the negative 3, then you do more of like this kind of this random search thing in like some area around that. And so usually, as you move on to different stages of the project, like the exact value of the hyperparameters that works best will change, but kind of the range hopefully shouldn't. Yeah.
In our particular case, we're collecting the data set.
Mm-hmm.
So when we do the distribution shift,
Yeah.
and we would try to address that. Does that mean that we should not be collecting the test parts of all the data until we get there, or should we try to incorporate it into the workflow?
Yeah, I think the way I would think about this is, so the distribution shift thing applies when it's hard to collect data that looks like the data you ultimately will care about evaluating on. If it's easy for you to collect and label data like that, then you should just do as much of it as you can. But if it's hard, then I would say, you should prioritize making sure that you have some data that as close as possible to the data that you ultimately care about held out, so that you can use it as like kind of a final arbiter of your model's performance. And then only once you have that should you like start adding data from that distribution to your training set. You had a question?
Yeah. So about the types of errors you get and the bias variance errors, how much of that is just empirical, like hey, how this model turns out, or do you have some intuition for mapping certain hyperparameters to like, oh, this affects bias more?
Yeah. So there are some hyperparameters that are like really just good for addressing overfitting, right? So these are regularizers. So changing the amount of dropout that you add and things like that. That's like if you're trying to prevent your model from overfitting, then that's the thing those are the types of things that you should be working on. For things like learning rate, it's a little bit more about affecting bias, but it can affect both. And for things like batch norm, it's like very much about both. So it depends on the hyperparameter a little bit. Yeah.
Should you always train your model on the entire data set, or should you just have like, say, you
Mhm.
And then if we do that, say that the error rate is not ideal, but then like the first thing we can try is to adding more training data to it, right? Maybe then, like I'm not sure which, should we try to refine the parameter or should we try to add more training data to it?
Yeah.
The parameter might perform better if we have more training data, right?
Mm-hmm. Yeah, so I think the way I usually think about it is, your first goal is always to get your training error as low as you want it to go. And in order to do that, you're allowed to make crazy simplifications to your problem if you want to, just as a starting point, right? Because really, the goal here is can we make anything work on this problem at all? Is our pipeline set up in such a way, and is this data labeled correctly that we can train any model, even if it's on a simplified version of our data set, to work well enough, right? And so that's in this addressing underfitting stage. And then usually what will happen is if you've made a lot of simplifications to your model and your data in this stage in order to get, in order to sort of overfit your training set, then what will happen is, the next thing you'll need to do is your validation error will be much higher than your training error. And then, typically the first thing that you should do there is think about adding more data if you can. And so, I guess the short answer is yes. I usually would start with a smaller version of the data set that you ultimately care about. And then, once you've seen that you can perform well on that, then I would start adding back more data. Yeah?
Should the smaller version of the dataset be a random sample from the bigger one, or should it be a toy example, like it's a classifier, 50% yes, 50% no, especially engineered fields?
Mm-hmm. You can do it both ways. I've seen people do it both ways. I think one thing, if you really, really want to simplify, you can try to simplify the problem itself. And so maybe, if you have 1,000 classes, maybe you can just focus on 10 of them at first. If it's less clear how to do that for your data set, then maybe you just sample uniformly.
And when we're trying to address distribution shift,
Yeah.
what's the right way to do that? Because in most real life ML, you don't even know what's the distribution
Mm-hmm.
data you're evaluating.
Yeah, so there's a slide in the talk about this, and I think the main idea here is just to try to do some error analysis. And so what I would typically do is I notice that I'm doing much better on my train validation set than I am on my test validation set. And so what I'll do is I'll go look at some examples of where it performs badly on my train validation set and where it performs badly on my test validation set. And then I'll try to identify cases, specific images where it seems to be making a type of error on the test validation set that it doesn't make on the train validation set. And those errors are sort of your gradient towards what types of data you should be adding to your training set. And so oftentimes what you'll see is there's just not enough dark images in the training set, or the distribution of labels in the training set is totally different than it is in the test set. And then you can go do targeted data collection based on that insight. Great. Any other questions on this? Mm-hmm. You can't figure out the irreducible error in your problem. And this is why baselines are so important, right? So if you have, the better your baseline, the baseline is a lower bound on how good you can expect your performance to get. And so the better baseline you get, the better that lower bound is. The lower that lower bound is. And so, if you have some way of just kind of judging what ground truth should be, if you can have really competent human labelers label a small data set and see what error rate they get, then that's kind of the kind of thing that you can use to get as close as possible to it. But you can never actually measure it. Yeah?
Just as a side question, is there any way to address the distribution shift if the data is not images? Let's say I can look at the data, but it's just a bunch of numbers, and I have no freaking idea what's different about this particular entry that throws me a little bit.
Mm-hmm. There are things you can do. There's sort of a class of techniques called domain adaptation, where you're actually sort of explicitly using the unlabeled data from the test distribution in a smart way that lets you do better on that distribution, even though you don't have labels there. You can also kind of like another thing you can do is just sort of measure statistics of that data. So you can look at the mean and see if it's more or less the same, and the variance, et cetera. But it's in general it's challenging. You can plot it. You can do t-SNE plots. Project it down into a lower dimensional space and see what it looks like. And so you can get you can reason somehow about like whether these distributions really look the same, but I don't think there's as good a way as there is for images or audio or text or anything that we can interpret. Cool. Great, so I want to move on and talk about homework before we dive into the debugging challenge. So quickly, just to review last week's homework, you all watched the troubleshooting lecture, collecting an initial data set for your project. How many feel like you have a good data set for your project to work with at this point? Okay, relatively small number. Post on Slack if you need help with this. I'm happy to sort of help brainstorm where you might look for a data set or how to go about collecting it. Is it for those of you that don't have one? How many is it because you actually need to go out and collect that data set and you just haven't gotten around to that yet? All right, so just a couple. So for the rest of you, it's just about finding the right one online, and you should get on that. Completing project proposal. I think we're still missing a few of these. For those that submitted them, today at some point, I will try to comment on them tomorrow. If you submitted them yesterday, then I have already commented on them. And so for this week, next week, the lecture is going to be on infrastructure and tooling. And so there's an infrastructure lecture to watch as a starting point. And then for your project, the thing that I'm hoping that people can do is to get some sort of baseline working end to end. So, you have your data set, or you should have had your data set. And so, the next step is to get some sort of evaluation of how well you can do on that data set without using anything crazy, right? And so for some of you, this will be really simple neural network. For some of you, it'll be linear regression. For some of you, it'll be some sort of heuristic or some result from some paper. But the important thing is just to have like some indication of what a baseline performance looks like. And you've all put suggestions there in the project proposal, and so I'll go through and comment on those. And that's what you should try and execute on this week. And then I'll give feedback on the outstanding project proposals. Any questions about the project or about the homework for next week?
You say end-to-end, is that just like you should have some SQL model that spit out the prediction and then we evaluate that? That's the end.
Yeah. So I think ideally what you would do here, if you can, is like if you're, in that question that said like what is the end result of the project going to look like? Some of you said, well, it's a web app. Some of you said, well, it's like an iPhone app or something like that. So ideally, what you'd do is you'd set up that whole pipeline, and then you just have some dummy model that can stand in for where your like super cool deep learning model is eventually going to go. And so then you can actually take the picture on your phone and see how well the results look with the baseline model. Understanding that the timeline might be a little bit tight for that, and if you have some sort of more advanced deployment, then it's going to take a little bit longer to set that up. The next best thing would just be to make sure that you can evaluate that, kind of your entire pipeline with a stand-in model on your validation set or your test set. Yeah.
Which our end-to-end thing be available somewhere online? Like,
Up to you.
And was there any? I think it was a question asked on Slack channel whether we would have any, instances available for us for training. Is there anything previous?
Yeah, so we looked into whether we can get resources for the whole class, and unfortunately, it doesn't seem like we're going to be able to. One thing that you should do is for GCE and AWS, they both have sort of credits available for, if you're new to those platforms. And so if you haven't used that yet, then like everyone on your team should, sign up for an account and make sure that you're taking full advantage of those credits. And if you're running into issues with it, then like please just ping Stephanie and I, and we'll work with you to figure out what the best way is to get some sort of resources. Okay. Up next is the debugging challenge. We're going to have about, let's see, so it's 2 before the hour, and I think we're supposed to start Lee at 7:45. Is that right? Yep. Cool. So let's spend about like 37 minutes on this. And again, we're going to do this kind of similarly to how we did last week. Just work together with people next to you. Hopefully you've all set up PyEnv this time, so we can like get right through that part, and then we'll kind of wrap up and meet back up and discuss kind of what your approaches were and what issues you ran into at the end. It is time to wrap up working on this project for now. But I encourage you. I intentionally put in more bugs than I thought anyone could find, like hoping, beyond hope, to be like pleasantly surprised that one person found all the bugs. I'm guessing no one did, but I would encourage you to just go through this on your own time. I mean, I think like sort of the takeaway from this for me is that debugging in TensorFlow especially, and in machine learning in general, is kind of something that you just need to get experience with. And there's tools and tricks and sort of tactics that you can use that I tried to cover in the lecture that you all watched. But in in practice, you need to try these things out yourself. And so I'd encourage you to keep going through it on your own time. But that said, how many were able to find at least the first bug? Okay, almost everyone. Yeah, we'll talk about that one in a second. And how many were able to get the code running? So you're able to find the first 2 bugs. Okay, still most. That's really good. And then how many were able to find like at least one more bug after that? Even find is okay. Yeah. Okay, so some. Did anyone find at least like identify 4 bugs? Yeah. Okay. 5. Got it. All right. So what was the first bug? Yeah. So pretty much everyone found this. How did you find it? Anyone want to kind of suggest like what your strategy was for fixing this bug? I guess it was obvious because it popped up when you first ran it. Read the error message, yeah. And then this is kind of like the strategy here. Like when I run into variable reuse issues in TensorFlow, is just kind of look at what TensorFlow is telling you is that you're creating the same variable twice in your graph with the same name. And so by default, TensorFlow complains about that because it's like you can't create the same variable twice with the same name. And that's actually kind of a helpful feature because you don't want to do that by accident. But what it means is that you need to go back and look through your code and look at where you're creating the same variable twice, and then make sure if you're doing it intentionally that you're reusing that variable the second time. What was the second bug?
So I guess one of the things you were saying was set reuse equal to true.
Mm-hmm.
That didn't work. I had to go to reuse equal tf.auto reuse.
Yep.
Is there a difference why one works for some people and not?
Yeah. So tf auto reuse is just saying it's basically saying ignore that error. So it's saying every time I create the same variable twice, just assume that I meant to do it, right? So that's useful if you want to get things running, but it can be a little bit dangerous because you can create the same variable twice by accident. Reuse equals true. The trick there is you need to pass it reuse equals true the second time only, because the first time you're not reusing it, right? The first time you're actually creating it from scratch. Okay, and then once you did that, you could get the code working, and then hopefully the next thing that you did was run it with the flag overfit batch. So a couple people found more bugs after that. What bugs did you find?
Reshaping.
Oh yes, yeah, we didn't talk about reshaping. So how did you fix the reshaping bug?
Well, so you explained it to me. The convolutional layers take 4-dimension shapes. And the next test layer expected 2-dimensional. So we want to keep the first dimension the same, and then make the second dimension just spread out like flat.
Yeah. So in ConvNets, at some point, if you want to use dense layers, you need to turn a 4-dimensional thing into a 2-dimensional thing. So that's why we're reshaping, and we had the dimensions of the reshaping wrong. Strategy for how to fix this. I think the best way to fix bugs like this is to just step through your model creation in a debugger. So you can throw in some IPDB statement and sort of catch the execution of your code as you're creating the model. Step through it line by line and just print things out and see if the shapes make sense. And so what you could have done is you could have stepped through the creation of that model and then printed out the shape of the tensor right before you reshaped. And you would have noticed like it's batch size times 7 times 7 times 64. And then when you reshaped it, you were getting something that was not the same as that. And so that's when that's where you go in and fix the dimensionality there.
And what sort of debugger can you use for TensorFlow?
I just use IPDB. There is TFDB, which I've played around with a little bit and should work better for some things, but I don't really use in practice. OK, any other bugs that people found? Yeah, so it wasn't using the dropout layer. That's true. Anything else? OK, good. Yeah, so I encourage you, again, there's all the bugs are listed in the sort of the README. And so I encourage you to just spend some time going through it on your own and look at those when you get stuck and see if you can fix them. But there's a lot of bugs there. I think the strategy that I would use if I was trying to debug this is, once you have the model running, then I would try to overfit a single batch. If you're not able to overfit a single batch, which in this case you won't be able to, then I would sort of start inspecting the code and figuring out places where there could be something that is causing the model to not overfit. And in practice, what you'll see here is that the loss actually doesn't go down at all. And so that would cause me to instantly think, well, if the loss isn't going down at all, then either I'm computing the loss function wrong or I'm taking gradients wrong, right? Because ultimately, even if you're doing sort of the wrong thing with your model, your loss should at least go in the right direction. So that's kind of my hint for the next part. Any other sort of comments or questions about this, or thoughts about like why is this so painful? Yeah.
When would you expect the overfitting to get you 0 error, and when would you not? I mean, it's not clear to me that you should expect that to be the case.
Yeah. So the place where overfitting will get you is when you're actually evaluating the performance of your model. So overfitting doesn't. One of the things that's challenging is that it doesn't manifest as a bug. It manifests as a gap between your training error and your validation error. And so if you have a small data set, or your model is really big, or or possibly if you have a bug, then you'll just see like your training error is way lower than your validation error, and then that's when you know that you're overfitting.
Yeah, no, I understand that, but you said that you should be able to drive the overfitting error to 0. And it seems like in general you're not going to be able to drive even your training error to 0.
So the thing that you should be able to drive to 0 is your error on a single batch, right? So for any reasonably sized model, you should be able to memorize the labels for one batch of data. Yeah, and so if you can't do that, then that means that you have a bug. But in general, you're right. Like if your training error shouldn't always go to 0. But you should just try to get it below whatever your target performance is, even if you're overfitting, and then move on to addressing overfitting. Yep.
That input scaling fixed the overfit, fixed the training at last time. I think that's a huge. I think because it becomes too small, I suppose, if you divide by 255 and then 255.
Yeah, totally. Scaling inputs the wrong way, or scaling inputs to loss functions the wrong way is a really common source of bugs because it's hard to tell. Like a lot of times it feels like you're doing the right thing and you've just done it twice, or you're passing something in that's mathematically correct, but it's the wrong function signature for TensorFlow. So those are the types of things to be very careful about. All right, there's one last announcement that I want to make about homework that I forgot to say earlier. For one thing that we want to do with this class is, for those of you that want to, we want to kind of feature your projects and like help you kind of get a job if you're interested in that, or just sort of get attention to your work. And so what we're going to do is we're going to create an online gallery. And if you want to opt into doing this, then please just send kind of a short bio to Stephanie, and be ready to have a headshot taken next week in class. So again, this is for those of you that want to like sort of be featured, I would encourage you to do this and just message Stephanie with your bio. Yep.
Just loop back. Once you get the code to run, when do you start to figure around hyperparameters instead of looking for, bugs in the code? Like you mentioned that there's going to be like optimizer errors.
Let's take this one offline because we're running a little bit over time. Cool. So next up we have our guest speaker for the week, who's Redden. So Lee started a company called Blue River Technology, which is a company that builds robots that use sort of AI and computer vision to solve tasks in agriculture. Sort of really cool, like actually putting robots in the world. And they got acquired a couple of years ago by John Deere. And before that, Lee has been kind of deeply involved in robotics and AI research at Johns Hopkins and NASA, Stanford, and other places. So we're really excited to have you here, Lee.